Hi, I'm Scott Nakwi. In this video, we're going to look at the forward displacement solution for planar manipulators. So by the end of this video, you should be able to solve forward displacement problems for planar manipulators. So the example we're going to use is the planar 3R manipulator, where R denotes a revolute joint. So this is a 3-joint revolute jointed planar manipulator. So here's joint 1, joint 2, and joint 3. All right, and it operates in the plane, hence the name planar. So in the forward displacement solution, we would be given vector Q, which is our joint angles. So it would be theta 1, theta 2, and theta 3. And what we're trying to find is the position and orientation of our end effector given those joint angles. So we're trying to find the X position, the Y position, and the angle of our end effector, which we're going to denote alpha. So we can make a note. We're trying to find vector X, which comprises our X position, our Y position, and our alpha. Okay. So for the planar 3R robot, we can use trigonometry to solve for the forward displacement solution. So we're going to start with the X position. And if we go back to our figure, what we're trying to figure out is what is the projection of our end effector position on our x-axis. And we can do that by finding the projection of each of the links. All right, just using trig. So the projection of our first link would be L1 times cosine theta 1, and that will give you this length here. So let's write that down. So we're going to have L1 C1, and in this course we're going to use shorthand notation. So we're going to, if you see C ij dot dot dot, that's just the same as saying cosine theta I plus theta j plus whatever number of angles we have. All right, so if you see C, we're typically talking about cosine. All right, so that's for the first link. Now for the second link, all right, you might think it's just going to be L2 times cosine theta 2. But remember, when we were defining our angles, we defined theta 2 relative to theta 1. So in fact, it's going to be the cosine of theta 1 plus theta 2 times L2. So we're going to have plus L2 C12 now. And similarly, you can do plus L3 C123 for the third link. And that is our position in the X. Next, we want to do the Y, and we can do something very similar, all right, except now we're projecting our link lengths into the Y axis. So we're going to use sine. So this first projection will be L1 times sine theta 1. So we're going to have L1 S1, and where S1 denotes sine of theta 1, so we'll make a little note here. So Sij would be sine theta I plus theta j plus whatever number of joints we have here. L2, again, we're going to take into account theta 1 and theta 2. So we're going to have plus L2 S12 and then L3 S123. All right, so now we have our X and Y position of our end effector given the joint angles. And the last thing we need is alpha. All right, and alpha, remember, is the angle of our end effector measured relative to our horizontal axis. Okay, and it is just simply going to be theta 1 plus theta 2 plus theta 3. So pretty simple. So alpha is going to be theta 1 plus theta 2 plus theta 3. And there you have the complete forward displacement solution for a planar manipulator. All right, and you can do something similar for different planar geometries just using trig.